Yeah. My name is Evgeny. I work as a researcher at JetBrains, and I'm going to present to you our joint work with Michalis Kakalonagis and Victor Vafiadis from Max Planck Institute for Software System. And the title of our paper is Model Checking for a Multi-Execution Memory Model. So first of all, a memory model defines semantics of concurrent programs operating on shared memory. Conventionally, we define semantics of such programs in terms of so-called execution graphs. So nodes of these graphs are program events, such as read or writes to shared memory, and edges of these graphs define various relations on these events. Two most important relations are program order that totally orders all the events from the same thread, and the reads from relation that connects a write event to all the read events that read from this thread. So we can see an example of a program and the three executions graphs of this program, and they correspond to various ways to execute these instructions of this program according to the order they appear in the thread. However, some memory models, for example, memory model of ARM processors, also assign to this program an out-of-order execution. This execution can be explained as a result of optimization that reorders a load instruction past the independent store instruction in the left thread. The problem is that unrestricted use of out-of-order execution can lead to undesirable outcomes, known as out-of-thin-air outcomes. So, for example, if we consider another program shown here, so note the difference here is that now both threads have semantic dependency between instructions. For this program, assigning the same execution graph would be a mistake, because now it appears out of thin air. There is no reasonable compiler or hardware optimization that can lead to this result. In order to distinguish between valid out-of-order execution graphs and out-of-thin-air execution graphs, modern programming language level memory models employ a multi-execution style. According to this style, multiple execution graphs can be used to justify single program outcome. So, for example, if we have a look at the weakestmo memory model, it encompasses multiple runs of the program into a single event structure. And the additional branches of this event structure are used to model speculative execution branches. So these multi-execution memory models, they serve the main purpose very well. Namely, they justify a soundness of a large set of various optimizations. However, they are extremely difficult to reason about, both for humans and for computers. In particular, if we have a look at the task of model checking concurrent programs under these models, which is in this setting equivalent to just enumerating the valid execution graphs, then this task is extremely computationally hard, and it is intractable even for simple programs. Indeed, generating in-order execution graphs is relatively easy because each such graph can be generated by enumerating its events according to some order that is consistent with program order and reads from. However, enumerating out-of-order execution graphs is much harder because now at each step we need to consider to perform a promise, that is to execute some store instruction out of order. And moreover, to avoid thin air outcomes, we also need to certify these promises. And that means that each promise should be backed up by some in-order execution that leads to this store to be executed. So these two obstacles significantly complicate the model checking algorithm and make it intractable in practice. In response to this, in our paper, we have proposed two novel properties for weak memory models. And together, these properties, they constrain the out-of-order capabilities of a memory model. And thus, they allow us to implement some optimization in model checker that improve its efficiency. Besides their use for model checking, these properties also forbid certain questionable program outcomes which cannot be explained by any combination of reasonable program transformations, yet they are allowed by some state-of-the-art multi-execution memory models, such as Weakestmo itself and Promising semantics. So in response to this problem, we proposed a novel revision of the Weakestmo memory model that satisfies these new properties and also preserve important properties of the original model, namely the dearth of theorems, sound compilation to modern hardware, and soundness of local program transformations. Next, we developed a model checking algorithm for our revision of the Weakestmo memory model, and we evaluated it on a number of benchmarks, showing that its performance is superior to few other tools for models that admit out-of-order executions, and it is even comparable to the best tools for models that allow only in-order executions. So next, let me present these new properties in more detail. So first is load buffering waste freedom, and it states that program can have out-of-order executions only if it has a load buffering race in one of its in-order executions. I'll define load buffering races a bit next. So for now, we can just notice that this property is equivalent to saying that if program is load buffering race free under in-order memory model, then it under multi-execution memory model, it has only in-order executions. So this property is very useful for a model checking algorithm because now it can operate as follows. It can start by enumerating in-order execution graphs, and it needs to consider to perform some promises only when it detects a load buffering race. This is a special kind of race between read and write, such that there exists a PORF path from read event to write event, starting with reorderable program at edge. And program edge is reorderable if there is, for example, no fence instruction between read and write. Next, in this case, the model checker operates as follows. It revisits the racy read and it removes all the subsequent events in program order of this read event, and then it tries to certify the promise by re-executing thread in question. If it succeeds in doing so, then we consider this is a valid out-of-order execution of a program. If it fails, then we discard it and move to the next execution. Another property that we have introduced is certification locality, and this property forbids various bait and switch type of behaviors. It states that speculative and actual branches of an execution should read the same set of non-local writes. So let me show it on another example. So consider the program, and again, suppose model checker starts by generating in-order execution graph. Next, it detects a load buffering race here, and it tries to certify the promise. The problem here is that the only way to do so, to certify this promise, is for the read from variable z in the middle thread to read value 1 that was written by the leftmost thread. And in general, it means that during the certification phase, the model checker may need to postpone execution of the thread in question and first explore some other parts of the program. And this exploration itself may involve more promises, more certification. And as you can imagine, this is computationally inefficient. Certification locality forbids this pattern, and it justifies it as follows. We forbid it because here we have a read event that reads from a write that wasn't observed by the speculative branch, and thus it is questionable program outcome. Certification locality allows model checker to perform certification immediately and quickly and locally by re-executing only thread in question. So for example, if we have changed the program as shown on the slide, then it would become possible to certify this premise because now this read in the middle reads from a local write. that was also available to the speculative branch. We have implemented our model checking algorithm that utilizes these two properties on top of GenMC. This is a state-of-the-art stateless model checker for the in-order fragment of C11 memory model. And we have compared its running time with a few other tools. So first we took GenMC itself as a baseline. Next, we took three tools, HMC, NeedHack, and RMM, which operate under hardware memory models. So these hardware memory models, they also allow some out-of-order executions, but they are not multi-execution in their nature. They use pair execution style and forbid thin-air outcomes by tracking syntactic dependency between instructions. It means that these models are simpler than multi-execution models, and generally they allow a smaller number of big behaviors than multi-execution models allow. Finally, we took two tools, CDS Checker and VMC itself, that operate under language level multi-execution memory models. You can see some data of our experiments on this slide. You can find even more data in our paper. So I'll just give a few basic conclusions that we made. So first, as you can see, the VMC performance is close to GenMC, and it's a good sign. Next, we noticed that for programs that have that are LB race free or have a few number of load buffer races, VMC, so these programs are located at the bottom of the table. For these programs, VMC performs better than all other tools, except GenMC itself, of course. And this is due to the fact that for this class of programs, VMC essentially performs the same as GenMC because there are not a lot of load buffer races. It doesn't need to perform a lot of premises and certifications. And also, as our experiments shown on in non-synthetic benchmarks, this is a quite common situation when load buffer races occur rarely. And finally, on some benchmarks, VMC performs slightly worse than other tools, but we discovered that usually this is attributed to the fact that it simply has to enumerate more execution graphs than pair execution models allow. So in conclusion, in our paper, we have proposed two novel properties for weak memory models that made model checking of multi-execution memory models tractable in practice. We presented our new revision of the weakestmo memory model and proved that it has these two new properties and also preserve the important properties of the original model. We have developed a new model checking algorithm for our revision of the weakestmo memory model, and we have evaluated the algorithm. That's all. I will be glad to answer your questions.
It's a bit of a high-level question. The way that I heard your talk is you had these ideas, you applied them, you implemented them, and you had great speed-ups. Was there some element of trial and error, or were you super lucky or super clever?
Sorry, could you repeat the last part of the question?
The way I heard your talk, it was that you had some ideas and then you implemented them and then you had great results. And I wonder whether that is how it happened, or whether there was some part where you tried different approaches, you had to refine the approaches, and then you got the result. So were you very perceptive and you had an idea and it worked out, or did you have to sweat a little bit?
Yeah, actually there was a lot of obstacles. So first, we actually started like this project to implement a model checker for existing models like weakestmo and Promising, using this approach with detecting load buffer races, as I said before. But we quickly discovered that the models, memory models that we check against, they do not satisfy this property that we needed for this approach to be sound. So it meant that we just not just implemented a model checker, but we had to refine these models, like to find the problems. We find that it's not that they just simply does not satisfy these properties, but the way they don't satisfy, like this give rise to these problematic behaviors that cannot be justified by compiler optimizations, and thus we had to refine the models. And then we also found that this first property about buffering with freedom was not sufficient, and we also need this certification locality property. So it wasn't apparent at first. We invented it during the work. Yeah. So we started with what buffering with freedom. Then we discovered that the model do not have this property that we need for the model checker to be sound. And then we also discovered that we need another property, certification locality. And that's how the story was.